Hey everyone. Today we're going to be talking about simple harmonic motion. So simple harmonic motion occurs whenever an object tends to return to a preferred equilibrium state whenever it is disturbed. So examples of systems that display simple harmonic motion include springs, pendulums, and molecular bonds. So it might not seem like much, but simple harmonic motion is one of the most important ways of modeling the universe that we have. So some of the most complex physical theories, such as quantum field theories and string theories, involve treating space like a collection of simple harmonic oscillators. So basically, we treat all of space like it's full of jiggling springs. And the results that we get from such theories are actually remarkably powerful, right? They usually have very good results. Now, that being said, we won't go into any sort of detail regarding any quantum field theory or string theory, because they're kind of outside the scope of this course, but we will talk about how we would model things undergoing simple harmonic motion. So to begin with, we will first introduce the idea of an ideal spring. So to begin with, I'm going to look at almost the quintessential simple harmonic oscillator, which is the ideal spring. So an ideal spring is any spring that obeys Hooke's law, but don't worry, we'll talk about that in a second. But to start with, we need to lay down a little bit of a foundation here. So let's pretend that this is some immovable wall, for example. And let's say that we have a spring attached to the wall, right? And on top of that spring, at the end of the spring, we have some mass, right? I'm going to call the position here x is equal to 0. So this is going to be sort of like a 1D problem, right? So this origin here is going to coincide with the equilibrium position for this spring. So the origin corresponds to equilibrium position. Right. Now the thing is, this equilibrium position is what the spring wants to do. This is where the spring wants to be when there's no external force acting on it. So if you just have a spring and it's doing its own thing, it's going to have some natural stretched length, right? And wherever the mass at the end of the spring wants to be, we call that the equilibrium state. So maybe I'll just write that here. So the relaxed state is the equilibrium state. Right? There's no external forces in our problem yet. So let's look at some properties of an ideal spring. Properties. All right, some properties. So if we stretch our spring, right, what does that look like? Well, when we stretch our spring, right, we're going to have, this is our x direction, right, this is our wall, right, this is what our spring is attached to. And let's say that, the equilibrium position is here. But let's say that our spring is stretched out to here, right? So this is going to be stretched out to some distance, which we'll call x. This distance right here, it'll just be x. And so notice that there's going to be two forces acting on this spring, right? So there's going to be an external force that's pulling this spring out, right? It's the thing that's actually making this thing like overextend and stretch. So this is the external force. And then because we're overstretching it, the spring is going to want to return to its equilibrium position. It always wants to return to its equilibrium position. And because of that, there's going to be a force towards the equilibrium position, right, towards x is equal to 0. And this is going to be the force exerted by the spring itself. we call the F sub S, right? And so if we're not looking at stretching, but instead, contracting, so contracting spring, right, then we've got a similar situation. We've got our x-axis, we've got some sort of wall that our spring is attached to, some fixed object. And let's say that, the equilibrium position of our spring is here, but our spring has been compressed. So now let's say that it's only here. So again, this is at some position X. Right. So in this case, because X here, or X is 0 here for our equilibrium state, anything to the left of this point is going to be negative. So in this case, this X would be some negative value. And just like before, there's going to be two forces acting on this spring, right? There's going to be, right, some external force that is trying to compress the spring. External, right? Because without this external force, the spring is more than happy to just sit out here. But because there's this external force, the spring is going to want to return to its equilibrium position. So in this case, the spring force is going to be pointing to the right because it wants to go back to relaxing, right? Don't we all? So the equation that describes the motion of an ideal spring is given by Hooke's law. So I mentioned earlier that any spring that obeys Hooke's law is going to be an ideal spring. Let me just zoom out a little bit. So Hooke's law like that. Hooke's law says that the force exerted by a spring is going to be equal to minus some number, k, called the spring constant, times the displacement of the spring in the x direction. There we go. Okay, so Fs, right, this is going to be our spring force. Right. Here, K is called our spring constant. Spring constant. So it's going to be, in units of newtons per meter. Right? And then here x is going to be our displacement from equilibrium. Like that. So x is our displacement from equilibrium. Right. All right, so let's look at a few examples using Hooke's law. So example 1. So example 1. Example 1 says that a spring has a spring constant. A spring has a spring constant of K is equal to 800 newtons per meter. And as a side note, I'm going back to this spring constant K here that we find in Hooke's law. This is going to be unique to each spring, so every single spring is going to have its own associated spring constant value. And essentially, the larger this spring constant value, right, the larger K is, the harder it is to either stretch or compress this spring, right? It's more stiff. So example 1 says that this spring has a spring constant of 800 newtons per meter. So it wants us to find the magnitude and the direction. So find the magnitude and direction of the spring force if A, we stretch it by 0.2 meters. We stretch it by 0.2 meters. All right, so this is going to be our displacement in the x direction. So we're displacing it basically 20 centimeters to the right. Part B is asking, find the magnitude and direction of the spring force if we compress it by 0.3 meters. Compress it by 0.3 meters. That's example 1. All right, to start with, let's look at part A. So part A, trying to find the spring force, a good place to start is to use Hooke's law, which is that the spring force is equal to minus kx, right, in the x direction. This is going to be equal to minus k, which is 800 newtons per meter, right, times a displacement of 0.2 meters to the right. So our displacement is going to be positive. Don't forget the direction. And here we see that the units of meters here get canceled out with the units of meters here. And then we're just kind of left with an answer in units of newtons, which makes sense because the thing on the left-hand side should be a force, right? The spring constant is really just a way of, it's like a proportionality factor between displacement on one hand and force on the other. So multiplying this all together, right, we get that the spring force that we get by stretching this particular spring by 0.2 meters is minus 160 newtons in the x direction. Right? So in this case, the magnitude for the spring force is just 160 newtons. And the direction is indicated by this minus sign here. So this minus sign indicates that it's pointing in the negative x direction. So minus x direction. So it's pointing to the left. Right, because we've overextended the spring, it wants to return to its equilibrium position. Right, so it's this case, we've overextended, and it wants to return back to its equilibrium position. So that's part A. Now let's look at part B. So part B, we're going to do the same thing, right? We're going to calculate the spring force of the spring when we compress it by 0.3 meters. So this is our Hooke's law. And now we just plug stuff in. So it's minus k. K hasn't changed. That's still 800 newtons per meter. Right? But now our displacement is 0.3 meters to the left, right? Because we're compressing it. So that's going to be minus 0.3 meters. Right? Where now this minus sign is going to be canceled out by that minus sign. So the force exerted by our spring is going to be equal to 240 newtons in the x direction. Right? So then the magnitude of this spring force is just 240 newtons. And its direction is just in the positive x direction. So it's pointing to the right. So this is the answer for part A, and this is the answer for part B. right, now let's look at example 2. All right, one more. So example 2 says that an ideal spring is hung from the ceiling. An ideal spring is hung from the ceiling. Right. So then, spring's just minding its own business, and then a 10 kilogram box is attached to the other side of the spring. Then a 10 kilogram box is attached to the end of the spring. To the end of the spring. So example 2 says that we slowly let the box stretch, or we slowly let the box stretch the spring. To its new equilibrium position. Which is 0.5 meters below the initial equilibrium point, which is 0.5 meters below the initial equilibrium point. Right. So the problem wants us to find the spring constant of this spring. So find the spring constant. Right. So let us sort of draw a picture here. So this is our ceiling. Right. Now initially, the spring is having a good old time. It's just hanging from the ceiling, living its best life. And then suddenly we attach a box to it, and then we let the box sort of stretch the spring out till it's at its new equilibrium point, right? And at neither point, right, here or here, is this box or this spring jiggling. So this is going to be our initial equilibrium point, and then this is going to be our final equilibrium point at that height. Right. So this is going to be our initial. This is going to be our final equilibrium point. So this is going to be right 0.5 meters lower, right? Because this distance here, 0.5 meters. So this is going to be minus 0.5 meters lower, right? Now there's like a box. Sorry, I know it's not like the most clear picture, but hopefully this sort of illuminates what's happening. So the box is being held up by the force of the spring wanting to return to its initial equilibrium point, but it's also being weighed down by the mass of this 10 kilogram box. So this is the weight of the box. Right, so mg. So the problem's looking at this, and it wants us to figure out what is the spring constant for this spring. So what we're going to do, we are going to look at a free body diagram of this box. Right, so there's our beautiful newly rectangular box. And so there's two forces acting on this, right? So there's the spring force pulling up, and there's the weight of the box pulling it down. And so if we use Newton's second law in the y direction, so Newton's second law in the y direction says that when we add up all the forces in the y direction, it's going to be equal to the mass of the box times the net acceleration of the box in the y direction. But the problem says we let the box slowly stretch out the spring until it's in its new equilibrium position. And then at that point, we don't want the box to be jiggling up and down. We want it to just stay at this sort of equilibrium point, right? So we want the acceleration in the y direction to be 0, which means that the whole right-hand side of this thing is going to be 0. Now, in this case, we have the magnitude of the spring force pointing up, and then we have the weight, mg, pointing down. It's going to be equal to 0 newtons. So we know that the magnitude for the spring force is going to be equal to the magnitude of the weight, right? But the magnitude of the spring force is just kx. Okay, excuse me, I guess k delta y, I guess, right? Because that's our displacement. What is the magnitude of that? Since we're looking at the magnitude for our spring force. And that's equal to the magnitude for the weight. And if we want to find k, right, we can divide both sides by the magnitude of our displacement in the y direction. So this gives us that our spring constant k is going to be equal to the weight of the box divided by the magnitude of the displacement in the y direction, right? So now we just plug stuff in. So the mass of the box is 10 kilograms. G is 9.8 meters per second squared. And the displacement in the y direction, its magnitude, is 0.5 meters. So punching all this into a calculator, this is going to give us a spring constant of 196 newtons per meter. Okay. 196 newtons per meter. Right. And that's the answer to our problem. So that's all well and good. But what if our spring is in motion, right? What if it's constantly jiggling back and forth across its equilibrium position? How would we go about describing its motion in this case? Well, one way to address this problem is by using the reference circle. So the next section we're going to be looking at is simple harmonic motion and the reference circle. Simple harmonic motion. And the reference circle. Right. So what is this reference circle? So first, let me just draw it, and then I'll talk about it a little bit. So first, we have our reference circle. Right, then I'm going to draw axes on it. So our y-axis, so our x-axis, the vertical axis is our y-axis. And so let's assume that our particle starts here, right? And let us assume that the x component here, the x component, is our position, for example, our spring, right? So let's say that the equilibrium position for our spring is here, but we stretch the spring out till it's right here. And then when we let it go, we want to be able to describe the motion of this thing as it sort of oscillates back and forth. Well, we can do that by using this reference circle. So this thing's called a reference circle, right? And we're really just using uniform circular motion here. All right, so it kind of makes it come back. Right. So let's say like at some little bit time later, as we go around this circle in uniform circular motion, position vector now looks like this, right? This distance here, right? This is our position. This is our x position, right? So maybe after we release it, right? After we release the spring, after we've stretched it, right? Now it's starting to come back. And after, a little bit, now it's right here. So we can describe this motion. Zoom in a little bit. So I'm just going to define a couple things. So please bear with me. This is the amplitude of our motion, right? And this here is an angular displacement theta. I just want to note that this position right here, we're going to say that this is the position of our spring at time t is equal to 0 seconds. So this is the position of our spring at times t is equal to 0 seconds. So this is basically how we're starting our system out. Right, it starts here, and then after t seconds, right, it travels this much around the circle, and its actual position, right, if we're in a laboratory setting, then its actual position is right about here, right? And as you go around this circle, right, its position is going to be, given by the x component of this triangle here, right? So as it goes around the circle, it's going to sort of oscillate back and forth as this thing goes around. And hopefully that's clear. So we can look at the displacement as a function of time, right? We can look at its position, for any given time. So it's displacement, right? The displacement of a spring or anything in simple harmonic motion is given by, right? If we're looking at its position in the x direction, that's just its amplitude times cosine of the angle theta that it's making on the reference circle. Right, so this should look very familiar. It's something we've already done before. It's basically how we're finding the x component for a vector, except now in this case, our vector's got a magnitude of a, the amplitude, and right, the x component is actually now our displacement in the x direction. So because this thing is going around in uniform circular motion, right, we're going to say that right now it's not accelerating, right? It's not going around, faster or slower. So it's at constant angular acceleration, which is 0. And because of that, we can say that the angle theta that it's making, with respect to the positive x-axis, is given by omega, or its angular velocity, times time. So how long it's been oscillating for. Right, so when t is 0, that means that our theta is 0, and that means we are a displacement of a away from our equilibrium point. So hopefully that makes a little bit of sense. So real quick. So if you remember, omega is literally just the change in our, or the angular displacement divided by the elapsed time. And this kind of gives us that our angular velocity in this case is just theta over t. Right, since we're saying that theta is starting from 0 when we're starting here. I'll also mention that here A is the amplitude of our motion. Right, A is for amplitude. All right. So taking this and plugging it in here, we get that our displacement x is given by the amplitude times cosine times our angular frequency omega times time. This is our first main result from this section. Right. So this literally describes the position of our simple harmonic oscillator. In this case, we're talking about springs, so it's going to be the displacement of our spring as a function of time, right? You plug in a time, and that'll tell you your displacement here, provided you know how fast, this thing's going around the this reference circle. But we'll do some problems, so please just hang in there. So this angular velocity right, of us going around this reference circle to sort of help us describe the motion as, we undergo simple harmonic motion. This angular velocity, right, is just how long it takes us to go around once. But in order to go around a circle once, that means we're going around an angular displacement of 2 pi radians, right, divided by the time it takes to go around once, or a period t. Right, so I'm literally just putting in, the definition that I mentioned. So right here, where again, t, like capital T, is the period of our motion. Right, so in terms of, a spring that's bouncing back and forth across its equilibrium position, right, the period is literally how long it takes it to be released and then go to one side and then return back to where it initially started, right? How long that takes is going to be the period. And so what we're going to do is we're going to define the frequency of this motion. We're going to define the frequency f to be equal to 1 over the period. All right, so this is the frequency of our motion. So if we know the period t, right, if we just invert it, right, do we do 1 over t, that'll tell us the frequency of this motion. So this is going to be in units of 1 over seconds, right? But units of 1 over seconds, we gave it a fancy name. It's called the hertz. So HC is just short for the hertz. Right? Okay, so what is the frequency and why do we even bring it up? So the frequency is how many times this thing undergoes a full revolution in 1 second. So let's say that you have a frequency of 2 hertz. That means that your thing, like your, whatever is undergoing simple harmonic motion, in this case, the spring, right? It'll go at its starting position. It'll go to their side and then back, and it'll do that twice in 1 second. If you have a frequency of 100 hertz, that means, your object is going to bounce back and forth 100 times in 1 second. And so the reason why I bring this up is because if you notice how we've defined this frequency is 1 over t. Well, there's this 1 over t factor here, so we can define the angular frequency with the same symbol omega. It's going to be 2 pi over t, but this is just 2 pi times our angular frequency. I know I'm throwing a lot of stuff at you guys, but I promise that once we start working through some problems, it'll make a lot of sense. I also encourage you guys to look at the supplementary material that I've posted on Blackboard, for this lecture. There's a lot of really good stuff in there. So if this is how we define our displacement for our bouncing, simple harmonic oscillator, right? It's either a spring that's bouncing back and forth, or maybe it's a pendulum swinging back and forth. Either way, we can describe our displacement from equilibrium by that. But now if we want to figure out the velocity, right, how fast is it going? It's velocity now. So we know that, let me just rewrite this here, that our displacement is given by the amplitude of the uniform circular motion times cosine omega t. So the velocity in this case, right, how fast it's going at any point along its low path, that velocity is minus a times the angular frequency omega times sine omega t. Right, so this is going to have units of meters per second. It's a velocity. So let's look at the max displacement that our spring can achieve, right? Or the max displacement that our pendulum can achieve, or whatever simple harmonic oscillator we're looking at. So the greatest displacement we can have, right, if you look back, right? So A is just a number, right? And cosine varies in value between -1 and 1. So the max value that x can take is when cosine is at its max value, but the max value of cosine is just 1. So the maximum displacement that our spring or pendulum or whatever can achieve is its amplitude A. And we can do the same sort of thing to look at the max speed of a simple harmonic oscillator. So the max speed at any point along this thing's trajectory is when we find the max value of this, right? But the max value of this, A is just a number, omega is just a number, and sine, right, also varies between -1 and 1. So the max value that sine can be is 1. So this ends up being equal to the max value for the velocity. So let's work a couple examples and see, if this sort of helps. So now we're going to look at example 3. So example 3. The diaphragm of a loudspeaker, the diaphragm of a loudspeaker moves back and forth in simple harmonic motion to create sound. Simple harmonic motion to create sound. Right, so usually for a speaker, there's like a tiny little magnet sort of in the middle, and what happens is, your computer or whatever sends a signal into your speaker, and it creates like little electric currents, which in turn pull the magnet to you, or not to you, but pulls it down. And by doing that, it sort of causes the loudspeaker diaphragm to like jiggle, and that creates pressure waves in the air, which we interpret as sound. So the problem goes on to say that the frequency of motion, is F is equal to 1 kilohertz. So this is 1,000 hertz. So it's basically vibrating at 1,000 times per second. Problem goes on to say that, and the amplitude is A is equal to 0.2 millimeters. All right, so we're gonna have to probably convert that. So part A is asking, what is the maximum speed of the diaphragm? What is the max speed of the diaphragm? And part B is saying, we're asking, where in the motion does this maximum speed occur? So where in its motion does this max speed occur? All right. So let me just sort of draw this real quick. So here is our diaphragm. Actually, let me switch to this. So the equilibrium position of our diaphragm is like this. And it sort of jiggles back and forth between like this and this, let's say. Right, so I didn't draw this very symmetrically, but this amplitude here, like this distance between right where it wants to be and where it actually ends up, this is A. We've learned that A is 0.2 millimeters. And furthermore, it sort of jiggles back and forth, right, 1,000 times a second. So frequency, it's 1,000 hertz. All right, and part A is asking, what is the max speed of the diaphragm? Well, we saw that max speed for something undergoing simple harmonic motion is just equal to the amplitude of the motion, right? How far this thing actually goes out, multiplied by its angular frequency. But we know that its angular frequency is just A times 2 pi f, right? And so now we just, input all this stuff. So first we have to convert A, right? Because that's 0.2 millimeters, but we don't want millimeters, we want, right, just regular old meters. So we know that there are, so in 1 meter, we know that there are 1,000 millimeters. This is going to end up being 0.2 times 10 to the negative 3 meters. And now we're just going to plug stuff into Vmax. Right, so it's the amplitude, 0.2 times 10 to the negative 3 meters times 2 pi times the frequency, which is 1,000 hertz. So multiplying all this together, this gives us a max speed, right? The fastest that this membrane is moving as it undergoes through this motion. That max speed is 1.2 meters per second, or 1.26 meters per second, excuse me. right, so this is part A. So part B is asking, where in its motion does this max speed occur? So if we set, for part B, if we set V, the velocity of this thing, equal to the V max value, right? We're just setting its velocity equal to its maximum value, right? The velocity is given by minus A times omega times sine of omega t. So this is going to achieve its max value whenever sine of omega t, whenever sine omega t is either plus or minus 1. Right? So that occurs whenever omega t, actually even let's back up a second. So sine of 90 degrees is going to be 1, right? Equals 1. You know that sine 270 degrees equals minus 1, right? And every single time that we add 180 degrees to our angle there, it's going to keep flip-flopping between plus 1 and minus 1. So this is going to correspond to a value of omega t being equal to n plus 1/2 times pi, right? Because pi is going to be 90 degrees, where n is 0, 1, 2, so on and so forth, right? So if you plug in 0 here, then you have 0 plus 1/2, which is 1/2, but 1/2 times pi is 90 degrees. So we've already seen that that works. If you put in 1 for n, then you have 1 plus 1/2. It's going to be 3/2. So 3/2 times pi is going to be, 3 pi over 2, which is 270 degrees. And so every time, you put in a whole number into here, you're going to get something, you're going to get an angle that makes sine, it's either going to be positive 1 or negative 1. So the location, right, where we achieve this max value is when omega t is equal to this thing. So if we're looking for the location, right, we're going to use our displacement equation. It's going to be A times cosine omega t. But we just plug this in. So this becomes A times cosine times n plus 1/2 times pi. But notice, might actually help to draw like a little circle. So notice, this is our circle. That's x, that's y. Anytime sine of theta is either plus 1 or negative 1, right? Cosine, right? The x component, something like this. The x component is going to be 0, and hopefully that sort of makes sense. So what this is saying is that the place where this diaphragm moves the fastest is when it's going through its equilibrium position. Right? So whenever it's going from one side and it's trying to get back to the other, as soon as it crosses over this equilibrium position, that's where it's moving the fastest. All right, so just like how we looked at the displacement and the velocity of something undergoing simple harmonic motion, now we can look at the acceleration. So the acceleration of an object undergoing simple harmonic motion. It's given by A, which is minus the amplitude A times omega squared times cosine omega t. Right, this also has units of meters per second squared. It's an acceleration. There we go. And so if you remember, the centripetal acceleration of something moving around in a circle is v squared over r. But in this case, the radius r is just the amplitude for our reference circle. That's v squared over a, right? This is going to be equal to a times omega squared. Right, we're sort of using the result. It says the linear motion is equal to the angular motion times the angular stuff, right? So we take this, plug it in here, and this is what ends up being spit out. So the acceleration of our object right? So if this thing is the magnitude for our centripetal acceleration, notice that that's precisely what we have right here. And so our acceleration is just minus the centripetal acceleration times cosine omega t. Right, this is like an alternate form. Right, so well, this and this are the same. So the max value that the acceleration can take here, max value is just right when this value here is it's at its max. But that's when cosine is at either +1 or -1. So the maximum value that this acceleration can take is the centripetal acceleration, which is just a omega squared. So let's look at another example. Let's look at example 4. Right, example 4. So for the previous example, all right, so we're still looking at the diaphragm. So for the previous example, this is example 3. What is the maximum acceleration of the diaphragm? Right, A max. And where does this maximum acceleration occur? So where does this maximum acceleration occur? Okay. Just as a reminder, the amplitude of this motion was 0.2 millimeters, which we found to be 0.2 times 10 to the -3 meters. And the frequency was 1000 hertz. So if we're looking at part A, right, we're trying to find the maximum value that A can attain. Right, what we saw, that's equal to the amplitude times our angular frequency squared. So this is just A times 2 pi f. We're squaring all that. Right, so when we just plug stuff in, so A is 0.2 times 10 to the -3 meters. Then we have 2 times pi squared. I'll just leave that off, I guess. Right, times 1000 hertz. We're squaring all that. And we get an A max value, right, the maximum value for the acceleration of this thing, of 7.9 times 10 to the 3 meters per second squared. It's 10 to the 3 meters per second squared. So this is part A. And part B is asking, well, where does this actually occur? So for part B, we know that our acceleration is equal to minus A omega squared times cosine of omega t. Right? And if we set the acceleration of like the diaphragm of the speaker thing equal to its max value, right, that's going to be equal to plus or minus A times omega squared. But we also know that A, right, the acceleration is given by minus A omega squared cosine omega t. So really, we want cosine omega t to be equal to plus or minus 1. Well, cosine of omega t is equal to plus or minus 1 whenever omega times t is equal to some whole number n times pi, right, where n is 0, 1, 2, so on and so forth. So if we were looking at this, through the reference frame of the reference circle, right, that's x, that's y. And so this right here corresponds to 2 points. It corresponds to here and here, right? Because if you plug in 0, 0 times pi is going to be 0, which is right there. Right, because keep in mind that this is theta. So when theta is 0, cosine of 0 is going to be 1. If you plug in 1, then theta is going to be equal to pi. So it's going to correspond to here. And cosine of pi is -1. So, if you keep flip-flopping back between these 2 points, which you get from here, then that'll tell you the maximum values. So for the location part, right, the location where this diaphragm is moving with max acceleration, right, is when omega times t is equal to some number times pi. Let's A, so cosine n times pi. Right, but this is just plus or minus A. So if I could go back up, it's like the little picture I drew, right? The max acceleration occurs whenever this diaphragm is at its maximum endpoints. So like here and here. At these points, the acceleration is so great because it wants to return back to its equilibrium position. So that's part B. So the max acceleration occurs at plus or minus A. So now let's revisit springs and, springs attached to walls and all that good stuff. For this next section, let's suppose that we have a spring. It's attached to a wall. All right, so this is the x direction. This is our wall right here. Right, the wall doesn't move. And we've got some spring. Let's assume now that's connected to some mass. Call it a block. Right, so this is some mass m. So let's assume that this thing is now in simple harmonic motion, right? So let's assume that it's sort of bouncing back and forth, right? Maybe we pulled on this box and we brought it out to here, and then we let it go, and so now it's just kind of bouncing back and forth. Let's look at how we can describe that motion. So if we look at all the forces acting on this box in the x direction, right, once we've let it go, that should be equal to the mass of the box times the net acceleration of the box in the x direction. But in this case, there's only one force acting on the box, and that is the spring force. So this is going to be minus kx. That's going to be equal to the mass times the acceleration of our box, right? But in the previous section, we learned that the displacement of an object that's undergoing simple harmonic motion is given by the amplitude of the motion, right? Like maybe this is the equilibrium position that the spring wants to be at, but we've pulled it out to here. Then this distance between its equilibrium position and the maximum displacement, this is going to be given by the amplitude A, right? So we learned that the displacement is going to be equal to A times cosine for angular frequency times time, t. We also learned that our acceleration is equal to minus the amplitude times our angular frequency squared times cosine omega t. So plugging some stuff in, right, we have minus k times x on the left. Looking now at this equation, we have minus k times our displacement a. So it's a cosine omega t. Right, and then on the right we have the mass of the box times our acceleration, which is minus a times omega squared times cosine omega t. Right, and so some things cancel, right? This minus sign gets canceled with this minus sign. This value of a gets canceled with this value of a, right? Because you can divide both sides. And cosine omega t cancels with that cosine omega t. And then we're left with, on the left-hand side, k, the spring constant for our spring. And on the right-hand side, we have m omega squared. So this is saying that if we know the mass of our object and the angular frequency of the object, then we can derive the spring constant. So alternatively, if we solve this for omega, right, the natural frequency of vibration for, a spring or a pendulum or whatever, that's going to be equal to, the square root of the spring constant k divided by the mass. So both of these are important, right? So this one is saying that if we want to increase our angular frequency, right, we just increase the spring constant. But if we're stuck with whatever spring they give us, then what we can do is we can decrease the mass. We can make the mass smaller, right? The mass attached to the end of the spring, and that will make our spring sort of bounce back and forth faster. So here, omega is the natural frequency of oscillation for our spring, right? So let's look at a quick example. So this is going to be example 5. So example 5. So example 5 says that a spring stretches by 0.018 meters when a 2.8 kilogram object, is suspended from its end. So it's suspended from its end, right? So this is a vertical spring. So how much mass should be attached to the spring? How much mass should be attached to this spring so that its frequency of vibration, is 3 hertz. Right. So we've got our ceiling, or whatever this is suspended to. We've got our spring that's sort of hanging down. It's got some mass hanging on the end of it. Right. And there's a couple forces acting on this mass, right? There's the spring force pulling up and the weight pulling down. mg, right? So when we sum the forces in the y direction, right, using Newton's second law in the y direction, we want its acceleration to be 0, right? Because it's not bouncing around yet; it's just hanging from the ceiling. In the part 2 of this problem, that's when it starts, bouncing around, and that's when we want to find, what mass makes it bounce at that frequency, right? So the sum of forces are: we have the spring force, magnitude of the spring force pointing up. We have the weight, the magnitude of the weight pointing down, 0. So we have kx is equal to mg, right? And so we can find, or I should maybe say ky. So we're dealing with stuff in the y direction. So we can solve this for k to find the spring constant for this particular spring, right? That's just mg over the magnitude of our displacement y. This is going to be 2.8 kilograms times g, which is 9.8 meters per second squared, divided by the amount that we're stretching our spring by, which is 0.018 meters, right? Just the magnitude of it. So this gives us a k value of 1,524 newtons per meter. Newtons per meter, right? Well, we know from the previous section that angular frequency of the spring is 2 pi f, but it's also square root of k over m, right? So what we're going to do, we know that we want f to be 3 hertz. So we're going to try and solve this for the mass that makes that happen. So what I'm going to do, I'm going to look at just this part, and I'm going to square both sides. So on the left, we have 2 pi f, square that. And on the right, we have the spring constant k divided by the mass. And so now I'm going to solve for the mass by multiplying it by both sides. And I'm going to divide this 2 pi f squared thing from both sides. So we get the mass. It's going to be equal to k, right, the spring constant, divided by our angular frequency squared. And we know that k is just 1,524 newtons per meter. And we want our frequency to be 3 hertz. So this is going to be 2 times pi times 3 hertz. 3 hertz. We're going to square all that. So this gives us a mass about 4.3 kilograms. All right, so that's the answer to our problem. Now, the very last topic that I'm going to cover today is called energy and simple harmonic motion. So energy and simple harmonic motion. So the gist of it is like this. We can store energy in springs or in pendulums if we lift them up, or in molecular bonds. Anything that can act as a spring can act as a storage space for energy. So if we have the spring, this is our x direction, say this is some sort of wall. Right, let's say that we have a spring. So it goes from, it's got a mass on the end, but it goes from, some initial displacement, right? And it continues on. Let's say we stretch it a little bit further. So maybe we stretch it out to like here or something, to some final stretched distance. I'm going to say that the distance between these 2 points, right, call it x. So actually I take it back. This is going to be our equilibrium point, but basically, however much we stretch our spring by, that's going to give us some potential energy. Right, it's actually going to give us a spring potential energy. So this is different from the gravitational potential energy. You can have both on a problem. So the potential energy of this spring is 1/2 times the spring constant K times your displacement of this spring away from its equilibrium position squared. Right, so the more you stretch the spring, or the more you compress the spring, right, either or, the more potential energy you can store. This is going to have units of joules. So now our total mechanical energy is going to look like this. So the total mechanical energy is going to be our kinetic energy, which is 1/2 mv squared, plus our rotational kinetic energy, which looks like that. Right here, this omega is not to be confused with our angular frequency that we saw earlier. This is when our object is like literally spinning. So that's that plus our gravitational potential energy plus the potential energy for a spring. Right, if you're not dealing with a spring, you don't have to worry about this. If your object's not rotating, you don't have to worry about that. If it stays at the same height throughout the entirety of its, motion, then you don't have to worry about this. So let's look at a quick example. So this is going to be example 6. It's going to be the last thing I show you guys. So example 6 says that a 10 kilogram box is attached to a spring with a spring constant of 1,000 newtons per meter. So the spring constant K of 1,000 newtons per meter. So at the initial time, right, the box is located at x is equal to -2 meters. It goes to -2 meters. And it moves with a speed of 10 meters per second to the right. It moves with a speed of 10 meters per second to the right. So the problem wants us to find. So for part A, it's asking us to find the magnitude of the velocity of the box when it reaches its equilibrium position. So find the magnitude of the velocity of the box when it reaches the equilibrium position of the box, and it reaches its equilibrium position. Part B is asking us for the amplitude. Find the amplitude. Amplitude A. Part C. Just kidding, there's no part C. So it's only part A and B. All right, so looking at part A, right, we want to find the magnitude of the velocity of the box, right, when it reaches its equilibrium position. So what we're going to do, we're going to use the conservation of energy to solve this. So I'm going to say that the initial point of this box, right, is when it's at, -2 meters, and it's moving with an initial velocity of 10 meters per second to the right. So in this case, the initial energy is just 1/2 times the mass of the box times the initial velocity of the box squared. The box is not rotating, so we don't need to care about rotational kinetic energy. It's at the same height, so we don't need to care about gravitational potential energy. Let's just say that it's on the ground. Who cares? But it does have a spring potential energy, so it's 1/2 k times x squared. Right. So this is going to be 1/2 times the mass of the box, which is 10 kilograms, times the initial velocity of the box. That's 10 meters per second squared. We have plus 1/2 times k. K is 1,000 newtons per meter, according to the problem, times x naught, which is just -2 meters. We're going to square that. So the initial energy of this thing is 2,500 joules. And so we're going to assume that energy is conserved in this problem because there's no friction anywhere. And we're going to say that the final position of our, we're going to say that the final energy of our system occurs when we are at the equilibrium position. So at equilibrium, right? At equilibrium, our displacement is going to be 0 because it's going to be at the equilibrium position. And we're trying to find the magnitude of velocity, so we're trying to find how fast it's going at that point. So just like before, our final energy is going to have some final kinetic energy, right? And well, actually, that's about it, because there's going to be no spring potential energy, right? Because this is going to be 0. So 0 squared is just 0. So the final kinetic energy is just 1/2 times the mass of the box. That's 10 kilograms times the final velocity of that box squared. Right, and using conservation of energy, we know that the final energy of our system is equal to our initial energy. So on the left, we have 2,500 joules. On the right, we have 1/2 times 10, which is just 5, right, times final velocity squared. So the final velocity of this thing, right, when we solve this, is going to be 22.4 meters per second. All right, well, you're going to notice that this velocity is positive because, we started from, right, so this is the wall, right? We started from here, the equilibrium position is here, right? So our initial velocity was this way, and we said that our final was over here. All right, so we found the magnitude of the velocity as it goes across its equilibrium position, and now we want to find the amplitude A. So for part B, we know that the maximum value for its displacement has to be the amplitude A, and at that point, the velocity has to be 0, right? Because it just reached that point and now has to stop and turn around and go back towards its equilibrium position. So, our initial energy is still the same, right, from this previous part, because that hasn't changed. But now let's say that the final position is when we're at x is equal to a, and our final velocity is 0. So in that case, the final energy of our system is going to be entirely the spring potential energy. Right. But since we're at x is equal to a, this is 1/2 times k, so a squared. Right. So on the left-hand side, you have the initial energy of our system, 2,500 joules. And on the right, you have 1/2 times k, which is 1,000 newtons per meter, right, times a squared. And if you solve for this for a, you get that this thing has a maximum displacement of 2.24 meters. And with that, we've completed the problem and we've completed the lecture. So I'll see you guys tomorrow.